Hey guys, want to talk about atoms today. What makes up atoms, how they behave, how they work. Not molecules, that's next time, but just the atoms themselves. So let me show you a little picture here. Nothing too surprising. You certainly know that there are protons, electrons, and neutrons that make up atoms, and those particles go in very specific places. The protons and the neutrons should be in the nucleus, the core of the atom there, while the electrons sweep around the outside in orbits, something like what you see here. We'll talk more about that in a little bit. But the protons are positively charged. The electrons are negatively charged. The neutrons are neutral. They have no charge. So those charges are listed here. Plus E means the charge of the proton. Negative E would be the charge of the electron. They have exactly the same number, but they're different, positive, negative. That's the only difference. Again, the neutron is neutral with zero charge. So you got a positive charge, a negative charge, and a no charge. The mass over here is a number that doesn't even make sense to the head. This is 0.2601673 kilograms. Okay, it's so small you can't even get your head around it. And very often we just call it 1 AMU. This AMU right here stands for atomic mass unit. And so that would be the mass of the proton is 1 AMU. You see down here that 1 neutron is also 1 AMU. So the proton and the neutron have almost the exact same mass. Not quite, but close enough. We're just going to say that the proton has a mass of 1, the neutron has a mass of 1, and the electron is so light, it's 5 10,000ths of an AMU. So we just call that one 0. 1 for the proton, 1 for the neutron, 0 for the electron. Meanwhile, in the charges, the proton and electron have the same charge. Only one of them is positive, one of them is negative. The neutron is 0. So see if you can keep up with that if you like. Those charges are important because it's the charges that pull each other towards each other. When you get a positive and a negative charge, there's an attraction there, and they're going to be attracted to each other. That's what pulls the electrons into these orbits, very much like the gravity between the sun and the earth is what keeps us in orbit. It's that same kind of idea, a little bit different force, but same idea. Anyway, how did we come to know this? Well, we call it the Rutherford model because this guy down here at the bottom, Ernest Rutherford, is the guy that came up with it. And the way he came up with it was he had a couple students, graduate students, and they were bored on a rainy day, snowy day, I suppose, and they needed something to do. So he sends them down the hall and says, hey guys, I want you to bounce some beta particles, some radioactive particles off of thin gold foil and come back and tell me what angle they bounce at, what the deflection of these things is. And what he fully expected was to take this piece of gold foil and shine these radioactive particles at it, and for everything to go off in pretty much a straight line. These things had enough energy to zip right through this thin foil and not be seriously deflected. And at the time, they used what was called the plum pudding model. We don't have plum pudding in this country. We do have chocolate chip cookies. We do have fruit cake. We do have raisin oatmeal cookies and things like that, where there's this big lumpy thing and there's chocolate chips distributed evenly, more or less evenly throughout it, or raisins or what have you. Well, in Europe they had plum pudding, and it was a big lumpy thing with plums kind of scattered about through it indiscriminately. And that was their idea of the atom. They knew that there were positive charges, knew they had negative charges. Let's just lump them all together. Well, they came running back down the hall, these two graduate students who were named Geiger and Mueller. The Geiger is the guy that made the Geiger counter, right? So he kind of went on with this, and I think Mueller did too. But what they said is, hey, boss, we're seeing some weird stuff. These beta particles, these little bitty radioactive particles, are bouncing back. They're being back reflected here. All kind of scattering angles. In actuality, some of these things were coming back. Here's his quote from what he said there. It's like you fired a 15-inch cannon shell at a piece of tissue paper. It came back and hit you. Totally blew him away because it didn't match the model. We love it when we find something in science that does not match our model, because that means we're about to learn something. And what he learned was that the only way that this could possibly work is that if these beta particles, which are small positive charges, it's actually 2 protons and 2 neutrons bonded together. If I had that small positive charge there come through and find a larger positive charge, then those positive charges would repel each other. So it would come in like this, and now actually the electro force there would cause that to just bounce back on its heels and deflect at some weird angle. All right, that was the experiment back in 1909 that got us thinking about all this and restructured the way that we thought about the atom. We still think it's that way. We found out more stuff about it since then, but that's our basic model. Now here, there are some numbers that I want you to know about. So let's see, trying to put this somewhere. The first number that I need you to know about is Z, the atomic number. I don't know why they call it Z. In German, the word for number is Zahl, and Zahl starts with Z, so I'm thinking that's what happened there. But all you need to know is that the atomic number is the number of protons. Okay? That's important because that determines what kind of atom you have. All right? If you could only know one thing about an atom, it would probably be this number. How many protons are there in the nucleus of the atom? Well, here they're using red to represent the protons, so we'd go through and we'd count. We'd say 1, 2, 3. And I'm going to write that number right here just so we can keep up with it. But the number of protons is 3. All right? The atomic number would be 3. And I could go to the table I'm going to show you in just a little bit here called the periodic table, and we could say, well, what is number 3? And we would have the answer. It's lithium, all right? But that's the first thing that we want to know about that. While we're at it, let's count up the number of neutrons and electrons. They're using these black circles to indicate the number of neutrons, and I've got 1, 2, 3, 4 that I can see. Let's assume that's all. There might be one in the back. 4, 5, maybe 6 or something. The number of neutrons can vary in an atom, and if you have the same kind of atom, namely atoms with 3 protons, then you might have 2 or 3 or 4 neutrons. Those can change, right? But those are in there. So we've got that number of electrons. I've got 1, 2, 3 of those. And in general, the number of protons is going to be the same as the number of electrons. If it's not, it's called an ion. Now that could happen, I've got my 3 protons. They're locked up in the nucleus. They're not going anywhere. But if I take enough energy and hit this guy, I could knock him off, so then I'd have 3 red protons and only 2 blue electrons. They're not really red and blue, that's just the color in the picture. But see how then it wouldn't be balanced? So that would make it an ion. And there are times when that happens. There are also times when it captures another electron. So now I'd have more negative charges than positive charges. That would be a negative ion. Whereas if I remove electrons, it would be a positive ion. Okay? In the picture here, I've got 1, 2, 3 protons, 1, 2, 3 electrons. That is normal, so this would not be an ion right there. Z, we already said, is the atomic number, and that's 3, so I'm going to put that right here. M is the atomic mass. And the atomic mass is what you get when you add the number of protons and the number of neutrons. Well, remember, each of these had a mass of 1 AMU. So if I go in here and say, well, I've got 3 protons and 4 neutrons, that gives me an atomic mass of 7 atomic mass units, like that. So it's really easy to work out what inside the atom, and there's all kind of ways that they measure how many neutrons there are, and it's usually an average number because that's going to vary a little bit, but the protons are important, and the electrons should pretty much match the number of protons to be a balanced atom. Now, these electrons that we're talking about, they have kind of assigned seating here. There are certain places that they're supposed to go, and we talk about electron shells. And this first shell right here, the one that's closest to the nucleus, that HS, I'm not sure what the HS is about there. Maybe that's the name of this thing, I'm not sure. But that's the nucleus. That gold ball in the middle would have all the protons and all the neutrons, and then the electrons are out here in various shells. But you can see that I can only seat 2 electrons in the first shell. I've got room right here, and I've got room for a second one right there. And when I hit 2, that shell is full, and I have to move electron number 3 up to the next shell. All right, and in that shell, I've got 1, 2, 3, 4, 5, 6, 7, 8 places that I can put an electron. The capacity for shell number 2 is 8. I'm not going to get any more in there. Okay, and that goes on out. You can see the electrons filling that thing up. There's a couple rules over here. The electrons travel around the nucleus. We talked about that. Only so many electrons per shell. It's like when you come to a classroom and there's only so many seats in the front row and only so many seats in the second row. It's the same deal. Once it's full, you got to move back, right? The inner shells have they fill up first, and the reason for that is, remember, the nucleus is positive and these electrons are negative, and they are attracted, they are pulled in to towards the nucleus. They're moving fast enough to stay in orbit, just like we're moving fast enough to not get pulled into the sun, even though it pulls on us in kind of the same way, different force, but that it's going to fill up the inner shells first, and this is a big one right here. This is a big part of what we're going to be talking about, especially on the next video. The atom really wants to have a full outer shell. Okay, a moment ago we had lithium. 3 protons, 3 or 4, 2, 3, 4 neutrons. That's all in the nucleus. All right, so there's the nucleus of this atom, lithium. I've got to put 3 electrons because there's 3 protons. So I'd put the first one in the first shell. I would put the second one in the first shell. That fills up the first shell, so I got to move to the second shell. And I've only got one more, right? 3 protons, 3 electrons. Here's electron number 3 right there. That does not have a full outer shell. Its outer shell is the second shell. There's only 1 electron in there, and that just burns lithium up. That just makes him so mad he can't stand it. All right? I can't really explain why. I'm not trying to anthropomorphize atoms and stuff, but they really want to have that full outer shell. It's something about the energy balance. It's kind of like when you're carrying a heavy suitcase, and it's almost better to have 2 heavy suitcases so that you're balanced up. It's that same kind of thing where it just works better. All right, lithium, this atom, is really reactive, and when we start talking about molecules, you'll see that he will do just about anything to get rid of that electron right there and become an ion, so that he can say, yep, I got 2 electrons in my outer shell. It's full outer shell. All right, but that's next video, so don't worry too much about that right now. These electrons can jump from shell to shell. Remember we said if you give them energy, they can escape the atom altogether, or they could jump up. So if I had an electron here on the innermost shell, and it gets some energy, like from radiation or ultraviolet radiation or some kind of picks up energy from electricity. You've seen neon lights. Well, that's what we're talking about here. That electron could jump up to a higher shell. The only thing is the electron is negative and the nucleus is positive, so it's attracted and it's going to fall back down to its original place. Or maybe something that was here in the third shell is going to jump down to the second. That'll jump, and the one that was here jumps down. These things kind of cascade and move around. It's a little bit fluid where they are, and they're all swarming around. They all want to get in close, and but extra energy is going to excite them, and they're going to jump out. But then they're going to come back in. When they do that, if something goes from shell number 2 to shell number 1, that's a specific distance and gives off a specific amount of energy. It took that energy to get it up there. It's got to give that energy back to get back down to the first shell. When you do that, that energy comes off in the form of light. And you might get this band right there. Okay? This is hydrogen. And when you look at the spectrum of hydrogen, it's got a couple blue lines, this light blue line, and a red line. That is the fingerprint of hydrogen. Hydrogen gas always gives off that signature right there, whereas calcium has these lines and mercury has those lines. When you look at this light, it has a very particular spectra, or spectrum would be the singular, and so you can see it. The means for doing that, here's a fluorescent light tube, right? That's almost all mercury. So here I've got a mercury light. The light comes off of that. You want to run it through a collimator, the little slit here, so that you're getting just that light. It comes back, and then you can either run it through a prism, triangular piece of glass, or a diffraction grating, which is a little piece of glass with a whole bunch of scratches on it. And when you put your eye up here and look at this thing, then through a little telescope, all this is enclosed in a box, by the way, then what you see are these lines. You don't get the full rainbow like you do when you look at white light. These optical devices here, the diffraction grating and the prism, will separate light into the full spectrum. But if it's a specific kind of gas, like hydrogen, like neon, you look at the neon lights in a restaurant or a bar or something, that's what they're doing. They didn't put neon on here, but neon has a lot of these red lines that come off and not a whole lot of anything else. And so that's why it's a red light. And you've got other gases that glow blue or green or yellow or something. You're looking at the spectrum, but more importantly, what you're doing is you're looking at these electrons jumping from shell to shell and giving that energy back off in the form of light. So it's handy. You can look at this light, you can look at the spectra, and identify what gases are in it just by measuring the wavelengths of these bands of light that come off. That's pretty neat. It tells us what's happening in the electron shells, and we can measure all these things and say, well, I see 1, 2, 3, 4, 5, 6 different energy levels coming off. So that means there's got to be 7 shells, and we can work out the energy levels of each one. Kind of neat stuff. Let's put all of that together, and this is what we call the periodic table. So the periodic table is a way to classify and to group all of the atoms together. And what you're going to do is you're going to start up here in the top left corner, and you can see that number 1 right there. That is the atomic number. So the simplest atom is number 1. It has 1 proton. It has 1 electron. We call it hydrogen. The symbol for it is H. And on average, it has an atomic mass of 1.008. Okay? Well, if it's got 1 proton and a neutron would be another one, that would give it a mass of 2. Okay? This is much closer to 1, so most hydrogen atoms only have 1 proton and one electron on the outside. There's my one proton, and one electron going around in a shell, and 0 neutrons. And I know that because I can take the atomic mass and subtract the atomic number and get on average how many neutrons there are. Let's try something else here. Over here is neon. This is the red gas we were just, the gas that gives off red light there. And you can see the atomic number is 10. The atomic mass is 20. I'm going to round that off to a whole number there. So if you take the atomic mass minus the atomic number, I'd have 20 minus, I don't know how to write these things, 20 minus 10, that gives me 10. This tells me there are 10 protons. This number right here tells me that there are also about 10 neutrons. And of course, protons and electrons have the same number, so I'd have 10 electrons there. And you could do that all the way down. You could work out what's going on. Now, it really was a little bit more than, this was 20.18. So I'd really have 10.18. That means about a fifth of the time I have one extra neutron. So roughly 80% of the time it has 10 neutrons. Once in a while you'll get one with 11 neutrons. It varies. Those are isotopes, and that's okay. All right. The periodic table is very handy because not only does it show the number of protons, the number of neutrons, and the number of electrons, it also shows how those electrons are arranged in shells. Remember how we had a capacity of 2 electrons on the innermost shell? Well, look at your top row. I've got hydrogen, I've got helium, 1, 2. Okay, and we had 8 electrons that could fit into the second shell. And so right here I have 1, 2, 3, 4, 5, 6, 7, 8. All right, and it gets a little more complicated after that, but the idea is kind of like that. This table is set up to reflect how many electrons there are in the outer shell, because that has a lot to do with how the thing reacts, how it behaves when it gets around other atoms. Specifically here, let's look at this last column. In this last column, all of these guys here as a group are called the noble gases. And when I think about helium, it's number 2, so it's going to have 2 protons, 2 electrons. Those 2 electrons fill that first shell. Helium is happy. He doesn't, he's got a full outer shell. He's not going to do anything. Here's neon. Remember that I had 2 in the first shell and another 8 in the second shell. 2 plus 8 is 10. Neon is number 10, so he's got a full outer shell. And this periodic table is nice because it actually shows right here that there are 2 electrons in the innermost shell, 8 in the second shell, and it's full. And that's all I have to do. Down here I've got 2, 8, 8. This guy's full. This guy's full. All the way down, the noble gases have a full outer shell. So they're all happy. They're not going to do anything to mix, to bond, to make a molecule. These guys never work out any kind of deal to get or lose electrons because they're happy. Okay? Meanwhile, we talked over here about lithium. Remember, he had 3 protons and 3 electrons. Put 2 on the first shell. That leaves 1 on the second shell, on the outermost shell. And that just burns him up. All right, he's got that 1 electron, and he's going to come over here and find one of these guys that wants 1 electron. There's 1 short. And he says, hey, man, I got an extra electron. Let's work out a deal or something. Okay? Here's sodium. Sodium's pretty bad, nasty stuff. If you throw pure sodium into water, it explodes. It bursts into flames. It wants to get rid of that one electron so bad that it's pretty unstable that way. Potassium, rubidium, all of these guys down here all behave kind of the same, and that's why they're colored red like that. They're called alkali metals. In the second row, I'd have one electron in the outer shell right here. I'd have 2 electrons in the outer shell here, 3 electrons in here, although see how it steps down, so these guys have 3. It gets a little more complicated as the table goes on, but the simplest view of it, you can see which column it's in, and that will tell you how many electrons are in the outer shell, and therefore how reactive it is, how bad it wants to make a deal. Carbon's kind of like, I got 4 electrons in the outer shell. I could lose 4, I could gain 4, I don't really care, whatever. But these guys on the end, not counting the noble gases, are really reactive, and they really want to cut a deal with somebody. All right. These 2 rows down here fit up into this. They need some more room. All of that blue stuff right there should be in here, which would step the whole table out so wide that it wouldn't fit on a piece of paper. So just for practicality sense, they cut these guys out and shoved them down here. But you can see the atomic number 55, 56, then you got to come down here 57, 58, all the way up to 71, where on it takes over again here, 72, 73, like that. And similarly, that green row would fit in right there like that. This is one way to show it. This is what you usually see, and you learn to work with it, and it works out fine. But it's always the same idea. Here's a nice one to kind of point out. This is number 80. It has 80 protons. Its symbol is Au, which is short for aurum, which means gold in Latin. This is gold right here. You can see it has an atomic mass of 196.97. Let's round that to 197. And that's its atomic mass, the number of protons plus the number of neutrons. If I subtract 80, I would get 117. If I did that right. Yeah, I think so. So gold there has 80 protons. It's got 117 neutrons. And you can see the shell configuration there, 2, 8, 18, 32, 18, and 1. All right? So that's a metal there. It's not too worried about that 1 electron in its outer shell, because gold's like so far down here. He's got 80 electrons he's dealing with, you know? And so it's kind of not as critical as it is for these guys up here in the first column. But that's kind of the ins and outs of the periodic table, and this is to me one of the great accomplishments of humanity, that we were able to take all of matter and separate it and say, on one sheet of paper, here's how the whole thing works. I think that's kind of neat. All right, so I may have already talked about all of this, but some more electron shell stuff. You can see that here we've got helium. Helium has 2 electrons that look like that. Here's neon. See that full outer shell? Argon is number 3, the third noble gas here. It's got a full outer shell, and so forth down like that. Here's lithium with 1 right there, and 2 for magnesium would be this guy right there. And, you know, it's kind of a good exercise to count that up. Magnesium has an atomic number of 12, so it'd have 12 protons, which means usually it would also have 12 electrons. You could come down here and see that it's got about 12.3 neutrons on average, but we're interested in those electrons at the moment. And so you're going to put 2 in the first shell. That's all there's room for. You can fit 8. 8 and 2 would be 10. So I'm up to 10. I got to get to 12 here. That leaves me 2, and those 2 would go right there and there. And that means I have 2 in the outer shell. Everything in this first column has 1 in the outer shell. Everything in the second column has 2 in the outer shell. And so that's just kind of all over again how that works. There's a little table on the right-hand side here that says how many electrons will fit in each shell. It's not quite fill it up top to bottom, but 2, 8, 18, you can see the numbers there. There is a little math formula for that. If you take the number of the shell and square it and multiply that by 2, then you'll get the number of electrons that'll fit there. The first shell would be shell number 1. You square 1, you get 1. Multiply by 2, you get 2. The second shell is 2. 2 squared is 4 times 2 is 8. 3 squared would be 9 times 2 would be 18, and you could go all the way down like that if you needed to. Now, I showed you the periodic table. I just put this in here for fun. I didn't actually know about this until I started building this, but there are other periodic tables. There are other ways that people have arranged this information, and maybe they have a different emphasis, a different thing that they're trying to demonstrate or something. But if you're interested in that, just type in alternative periodic tables and look up the Wikipedia page, and there's a bunch of neat stuff about that. They're just kind of interesting to think about the way we arrange information to look at it. Here's some other ways. All right. Now, inside the atom, lots of things can happen. We've got these protons and these neutrons. Sometimes they get a little quirky. All right. Whenever my wife sends me to the grocery store, she says, "Hey, can you go to the grocery store and get some milk and some bread?" And I go, "Yeah, sure." And I walk in the grocery store and go, "I'm only getting 2 things. I don't need a cart." And I go get the milk and I get the bread, and I get back up to the line, and right about then the phone's going to ring, and she says, "Oh, I also need you to get some salt and some flour and see what if there's any squash on sale." Okay? Well, I've already got the milk and the bread, and now I'm trying to hold all this other stuff, and at some point I start dropping things, right? And that's kind of what's happening here. When you have these radioactive decay states, then it's because there's too much going on, and the atom can't hold on to all those particles. Kind of like you're dropping the loaf of bread because you got too much in your hands. Well, there's 3 main kinds here that I wanted to tell you about. You got alpha decay, which is going to spit out an alpha particle. That's the thing that Geiger and Mueller and Rutherford were doing. Here's an alpha particle right here. It's 2 protons and 2 neutrons. So effectively, it's the nucleus of a helium atom, but it could come from something much bigger, let's say uranium. Okay? And uranium gets a little tired of holding the bread and the milk and the squash and the grapes, and something falls out. And that means that the nucleus of this atom has changed. It now has 2 protons fewer and 2 neutrons fewer. Here's some symbols that you can do. X could represent any element. If it were uranium that we were talking about, then you'd put the symbol for uranium, U, and you'd have the atomic mass right here and the atomic number, and it decays into this alpha particle right here, which has 2 protons and an atomic mass of 4. So 4 minus 2 would be 2 protons, 2 neutrons. And you've got to take off 4 from the atomic mass and 2 from the atomic number, and there'll be something new here that it would turn into. And you can go back to the periodic table and you could say uranium is right, where'd they put it? Let me go back to the other one where I can see the whole thing. Shoot, I want to say it's 80. Where is it? Well, phooey, I don't remember where. Oh, it's down here, I'm sorry. Uranium is 92. So if I had an alpha decay and an alpha particle came out, that would take 2 protons and 2 neutrons, and it would kick it back to thorium right here. 92 minus 2 would take me to thorium. So, this instead of, if this is uranium, then this is going to go to thorium right there. And where this was 92 and 197 or whatever the numbers were, then it would drop it down to 193 and to 90 right there. And you could work that out and see what's going to happen. That's kind of interesting that that can happen. Here's a second thing that can happen. I can have something called beta decay. Beta refers to a fast, energetic electron. So this is kind of weird here, but one of these neutrons could spit out an electron. Remember, a neutron is neutral. This is negative. So if a neutral thing spits out something negative, then that's going to leave behind a positive thing. So that neutron just turned into a proton and spit out an electron. That's kind of weird, but you can see how the negative thing and the positive thing would cancel out and give you a neutral thing there. So that's a possibility with this radioactive decay that we're talking about. I could also get a positron. Here's an electron. I could have a positron get spit out. That would be a positive particle. And if this proton kicks out the positive part of itself, then that's going to leave it neutral. It's no longer going to be positive. It went neutral. So basically right there, a proton turned into a neutron. And now you've got this positron floating around. That's kind of weird. Maybe there's a proton and a fast electron makes it down in there, and the positive charge here and the negative charge here cancel each other out, and I get a neutron there. So a proton turned into a neutron when that electron got captured. And lastly, there's gamma decay. Gamma is electromagnetic radiation. It's a wave. So right here I could have a particle that goes and spits out this gamma ray. It spits out some energy, and it's kind of like an X-ray, a little bit higher energy though. That doesn't have, there's no protons involved, no neutrons involved. So right there the gamma has 0, 0 on atomic number and atomic mass. But I do get a different element over here. It does change it up with the thing. Okay? You don't need to know a whole lot about that, but we are talking about the atom and what happens in the atom, and these are some possibilities. And particularly when you see some of these atoms right here, uranium, plutonium, carbon, lithium-8, radon-220. This would be uranium is number 92, but the kind that has 238 atomic particles, or protons and neutrons with an atomic mass. So here's the element, but the mass is 238. That's got a whole bunch of neutrons. That's like holding a whole bunch of grapes and milk and bread, and it starts dropping things, and you're going to get that decay. Half-life is how long it takes for uranium to lose half of its radioactivity, to turn from uranium-238 into thorium, or depending on which radioactive process we're talking about here. And you can see the half-lives over here. Uranium takes 4.5 times 10 to the 9 years. 4, 5, 0, 0, 0, 0, 0, 0. That's 6, 7, 8, 9. Let's see if I got all those right. There's 3, 6, and 9. All right. That's a lot of years. We use uranium in our nuclear reactors. When we have used it to the point that we've gotten all the energy that's economically feasible out of it, then you take it out of the reactor core, and you have this radioactive waste that can no longer work in most of the nuclear reactors that we have in this country. There is a breeder reactor that you can kind of recycle it with, but you've got to store that thing for what is that, 4,500 million years for it to lose half of its radioactivity. So if you're starting here at 100%, then after all these many years, you have fallen to 50%. And in that much time again, you're going to lose half again. So it would go from 0 to 50. And in that much time again, it's going to lose half of that. So 50 down to 25%. And then in another 4,500 million years, you're going to be down to 12.5%. This is kind of like when you get a cookie and you eat half of it the first day. You said, man, that was good. I want this cookie to last. So you eat half of what's left the second day, right? So you ate half of it. Then you ate half of the half, which would be a quarter. So now you've eaten 3/4 of it, or you're down to 25%. And then you eat half of what's left. You're down to 12.5%. And see how you can make that cookie last a long time, but you have less and less cookie each time, right? The half-life is how long does it take to lose half of the radioactivity of it. And all of these guys do this. Some of them are super long times. Right here, radon 220 takes 52 seconds. Lithium is less than lithium 8 is less than a second. I'm not sure how lithium 8 got on here twice. I'm betting that's a typo. But you know, it kind of depends on what you're talking about with this thing. But this is pretty useful. Carbon-14, for example, has a half-life of about 5,570 years, and everything that is living has carbon-14 in it. Every time you breathe in, every time you eat something, you get more carbon-14 in you. It's okay, it's radioactive, but it's not that much and stuff. But we can count how much carbon-14 there is in somebody. It's going to turn into carbon-12. So carbon-12 is the normal stable kind. As carbon-14 turns into carbon-12, then you've got you know, that radioactive decay there, and it takes about this long to do it. Well, if I go dig up a bone or a pair of moccasins or anything in an archaeological site, and I find that there is 17% of the carbon-14 that's normally around, that tells me immediately how long that thing's been dead, or how long it's no longer been breathing in and eating carbon-14. We started out here at 100% when you died, you fell to 50%, fell to 25%, we're down to 17%, and you could use an exponential decay equation, something that you may have done in an algebra class, and see exactly how many years it would take to do that, knowing that it takes 5570 to lose half of what you did right there. So there's all kind of practical applications of this stuff, but not to mention, if we have some radioactive waste, how long do I have to store this before it's safe again? If you in Russia, there was a reactor called Chernobyl, and the thing blew up. They were managing it terribly, and it was totally their fault. But they do their reactors way differently than we do. But you know, this city blew up, and you know, they still can't go there. You still can't live there, and so you could go and see what kind of damage you'd have. All right, I wanted to talk a little bit about, because we're talking about atoms, two things. These are not chemical changes. These are nuclear changes here. One process is fusion, and basically if I take something very small, very light, like hydrogen, then we can combine that together and end up with something bigger called fusion. So these are small things making bigger things. And right here, for example, if I take these two hydrogen atoms, basically two protons, I get a reaction right here. I'm throwing off what's called a neutrino and a positron. That's going to turn one of these guys into a neutron. So now I've got this unit. It's a proton and a neutron. And then it can happen again, take a proton and this new thing right here, throw off another neutrino, and now I've got two protons and a neutron. And I could do it one more time, end up with 2 protons, 2 neutrons. That's what we call an alpha particle, or a helium nucleus. All right. And so it takes that whole big process. All of this has got to happen not simultaneously, but in order to make that happen. And fusion's pretty neat. This is what's making the sun hot. This is what gives us all the light and heat to happen for life to exist here on Earth. As soon as the sun stops doing this, it's going to get very cold and very dark in about 8 minutes from when it stops, and all life is going to die. Okay? Now, it's not going to do that for millions of years. You don't have to worry about this. Okay? But this is an important process in the universe. We wouldn't have stars, wouldn't have light, wouldn't have heat, wouldn't have life or anything without this going on. We can do this process on Earth, but it's not economically feasible at the moment. We can't get, it takes more energy to do this than we get out of it. So right now, all of our nuclear reactors are the other kind, fission reactors, and I was going to show you that too. But this is a neat process. If we could get this to work and generate power with it, we got, water is made out of hydrogen, right? We've got plenty of hydrogen, and we could turn it into helium, which is a noble gas. It's not poisonous. It's not reactive. That would be kind of that would solve all of our energy problems forever. So they're working on that. We're getting closer, but not there yet. Take something small, make something bigger. Here is the fission reaction. I could have something big like uranium, and it breaks down into smaller particles, smaller atoms with fewer protons and neutrons. And so this is taking big and breaking it into little things. That gives off a tremendous amount of energy. Right here, fusion is taking little things, mashing them together, making something bigger. That releases a tremendous amount of energy on both of these. All this energy comes off, and whatever you do with that right now, like our fission reactors, we take all that energy, we boil water, make steam, steam turns a turbine, turbine turns a generator, generator makes electricity, right? So that's happening around the world right there. Here's a little bit of information about the fission, but I don't know there's a whole lot else to say. Our fission reactors typically take fast neutrons, and they come in here. That fast neutron breaks into a nucleus, and the nucleus says, hey, come on in. But that's like giving it that one more bag of potato chips. It's just too much, and it starts dropping stuff, and it separates here into two things. More neutrons come off when you do that. So there's usually two big chunks, a whole bunch of energy released, but some more neutrons, and guess what? There's another uranium atom sitting right here, and the whole process happens again and again. It's a chain reaction, and you got this happening all over the place. Each individual releases a bunch of energy, but you put all that together, and it's a lot. Okay, so that's what I wanted to tell you about atomic chemistry, and the atom and the periodic table are the most important parts of all that, and I hope that makes sense. Thanks for stopping by. Have a great day.